Welcome to Physics Department Conclave 2025, organized by the Department of Physics, IISER Pune. I'm G.V. Pawan Kumar, one of the professors at Department of Physics, IISER Pune. The important aspect is the theme of this particular conclave, which is contemporary questions in physics, the important and the interesting. Over the next 1.5 days, now we have lined up some very fascinating panel discussions and poster presentations. The last count of the posters were roughly about 85, and we probably expect even plus or minus 5, or plus on the plus side, hopefully. So the format of this particular meeting is slightly different from the conventional meetings what you would have come across, especially in the context of physics meetings at the department level. The format would contain two important elements. The first element is the panel discussion. The other one is the poster session. In the panel discussion, which lasts roughly for a duration of about an hour, in some panels, maybe this number may actually shrink, as we're going to mention. In 1 hour of this panel discussion, there will be an opening 10-minute overview of the questions, what the panel members are interested in and pursuing. Subsequently, the other 30 minutes would be mainly on the discussion related to the questions what the panel members have already kind of given an overview of. And the last 20 minutes, which is very important, will be related to an interaction and a Q&A session with the audience. So that is one particular aspect which we strongly encourage all the students to take advantage of, not only the students, but also everybody who is part of the audience, to have an interaction depending on the particular questions what have been already discussed in that particular panel. So in that way, the whole 60-minute actually is well utilized. And of course, discussions can be taken outside into the various different sessions, which is the other important element of this particular conclave, which is the poster sessions. The poster session, although there has been an assigned times for these sessions, in principle, the poster sessions are for all the 2 days of this particular meeting. So if somebody wants to really have an interaction related to the posters, you actually can bring them either early in the morning, late in the evening, anytime. All the posters would be there on that particular poster board. So please feel free to interact as much as possible and foster kind of exchange of ideas. Other aspect I have to mention, which is very important, the housekeeping. Especially we may have people, few of them from outside. The safety aspects, there are 2 exits here, as you can see, but there are also 2 exit doors on the back. If you can also use them, especially during the discussion session, it would be better because it might not actually perturb the discussions and other things. Ensure that you actually do not kind of accumulate at the exit points. That is another important aspect. The water would be generally available outside the rooms. And if you need any other assistance, our volunteers would be around, and they'll be very glad to help you out. The other aspect is that there will be small snack breaks during this kind of discussion sessions. For example, today at 5 p.m. there will be a snack break, where we'll also have, in addition to the poster sessions, some chai samosa kind of stuff. Please make use of that particular opportunity to not only take food for thought, but also for your stomach. That is equally an important part of this particular meeting. Generally, people are thanked at the end of the meeting, but I don't want to do that, or I not only don't want to do that, I want to also thank a lot of people right at the beginning, because there's a lot of work which goes right at the front. The most important aspect is that a big shout out to all the student volunteers, our PhD, IPhD, and 5th year BSMS students. This meeting would have not happened but for their efforts. Thank you very much. I should also thank my outreach committee members, Ushashi Roy, Deeptamai Ghosh, Ashish Arora, Surabhi Jaiswal, and all the faculty members in the physics department who readily agreed to actually be part of this particular meeting. Thank you very much, because this was at a very short notice, and I'm extremely glad to see the response from our colleagues. In fact, so much so that many of our colleagues are also presenting posters. Catch hold of them, interact with them. Thanks, Mahesh, also, the chair of the department, who actually has been very encouraging and supporting, both intellectually and monetarily. Okay. Okay, now coming to the business end of this particular meeting, which is very important. So, what is the reason for why we are doing this conclave? That is an important question we have to address. As you know, in physics, we study the subject by listening to lectures and solving problems. This is the general pathway we generally take. A few questions remain. That is this sufficient enough to actually obtain knowledge for our greater understanding and also to foster our research? Is this only the effective way of learning and teaching physics? Roughly around 1963, Richard Feynman, writing in his preface of his famous lectures in physics, had to say the following, quote, "The best teaching can be done only when there is a direct individual relationship between a student and a good teacher. A situation in which students discuss the ideas, think about things, and talk about those things. It is impossible to learn very much by simply sitting in a lecture or even by simply doing problems that are assigned." Stop quote. We are in an AI age, which means that this becomes even more important. Therefore, with this motivation of talking more physics, this conclave actually has been organized in such a way that we foster the conversation in physics among everyone who is interested in physics across the subdisciplines. I hope all of you will have a thought-provoking time over the next 1.5 days, and it will intellectually stimulate us to explain physics and explore physics that we all love so much. After all, human progress, both the intellectual and the materialistic progress, are intertwined with the progress of physics. And at the heart of this particular progress is the contemporary questions in physics, and those questions which are not only important, but also which are interesting. So have a great physics conclave by learning about interesting questions and also by asking many, many questions, which is equally important for all of us to really foster as scholars, students, and in any form of human endeavor. Okay, so let's have fun, and welcome to Physics Conclave 2025. So the latest updates on the Physics Conclave can be accessed on this webpage, which has been extensively circulated among all of you. Please look up these kind of schedules. There might be minor changes, especially in terms of the timings and also the committee, the panel members, which actually will be updated live. Okay, this is one web page where you will find a lot of information which is updated. Of course, we'll also be informing you if there are specific changes as and when we discuss more. So with this, you also probably will see that there are some very interesting sub-disciplines of physics which have been actually slotted into to the panels, starting from astrophysics, atomic molecular optical physics, advanced materials, and tomorrow, which actually is also the longest day of the particular meeting, starts with particle physics, quantum materials, and here probably we'll have small variations in the panel 6 and 7, depending upon how long we can have the lunch break. We are trying to see whether we can have a longer lunch break. So that is something which we are planning. So do look at the schedule later on. And of course, there'll be some very interesting stuff related to theoretical high energy physics and gravity. And we'll end with our own quantum science and technology discussions. So if you click at underneath every particular panel, you would actually find people who are part of that particular panel. This is kind of updated, but there might be sometimes changes in this particular panel, the members of the panel. So please feel free to interact among yourself. Let it be informal, but also as much as possible interesting in the form of the discussions, whatever you have. And please don't hesitate to ask specific questions related to the meeting through our volunteers or any of our committee members. We would be glad to actually help you out. So again, I have to reiterate, just ensure that the safety aspects are taken care of. The exits are clearly mentioned. There are also 2 doors behind. So just pay attention to those things, which is important for us to be aware of. We are all set, and I'm very glad to actually now call upon our first panel members, which is related to astrophysics and cosmology, and this includes Prasad Subramaniam, Susmita Adhikari, Arko Banerjee, Deeptimai Ghosh, Sachin Jain, and Arun Talabe.
Thanks, Pawan, for organizing this, and welcome to the Astrophysics and Cosmology panel. This is a slightly diverse panel because astrophysics is the application of physics to study initially stellar objects and then many other astrophysical objects. And then cosmology is the study of the evolution of the universe as a whole. So this panel will cover a wide set of length scales. So I'll just take a few minutes to set the stage for how these length scales are ordered and what sort of science we can do at each of them. So astrophysics, of course, starts with trying to apply the principles of physics to our sun, which is roughly 1 AU away from us. Then if you look further out, you see other stars, of course. If you use a telescope, you can zoom in on those other stars. And you try to see if the same principles of physics that you apply to the sun also works for the evolution of other stars and so on. But as you keep looking further out, there are other things in our galaxy. You can see our galaxy as a whole, where there can be stars, there can be gas, there can be other exotic objects, there can be a dark matter, there is a dark matter halo. So you can explore, on scales of our galaxy, you can explore not only what's happening with the stars that's visible, you can try to come up with models for what is happening with dark matter, exotic objects, and so on. And this is happening on scales that are many thousands and millions of times larger than our distance from the sun. Okay? If you look even further out, you'll see that our galaxy is only one of many galaxies in the universe. Each of these galaxies around us have their own dark matter halos, have their own stars. So again, on those scales, these are again scales of roughly megaparsecs or so on, is again another test bed for our models of dark matter, our models for galaxy formation, what's called gastrophysics, and so on. Then if you look even further out, you'll see that these galaxies that we see around us are not ordered randomly. There's a pattern that emerges, which is called the large-scale structure of the universe. And this emerges on scales of, let's say, 200 megaparsecs or so, okay? Up to gigaparsecs. This large-scale structure is actually created by gravity acting on a set of initial conditions. And by studying this system, you can learn about things like the origin of the universe, dark matter, dark energy, various particles that make up our universe, and we'll get into this in more detail later. Then finally, you come to the edge of the observable universe, which is roughly 10 gigaparsecs. So we've already spanned about 15 orders of magnitude in length scales. And this is where you have the cosmic microwave background, the farthest light that you can ever possibly hope to see. And this is precisely what tells you about how our universe started, maybe how it will end, and so on. Okay? So today's panel, we will try to cover various aspects of this picture. But it also so happens that because of the initial conditions of our universe, you can flip the order of this picture. So if you think of how the universe itself evolved, what happened was initially there was a period of inflation. Then you have various elements forming in our universe. Then the cosmic microwave background radiation being emitted. Then you have a period when cosmic fluctuations grow. The first galaxies and stars start to form. And then we are at that last point there, 13.82 billion years. And in this picture, what happened during inflation and the early universe actually happened in a universe where things were much hotter and denser, and the relevant physics was happening on very, very short scales. So in this picture, the early universe is where you probe very high energy physics, And then if you go forward, you look at stars, evolution of or stellar evolution, you're actually looking at more classical physics, okay? So you can keep these two pictures in your head. We will go in order of this later picture. And we will sort of go in order of what comes first in here. We will start with Diptimoy, who will tell us about inflation. By the way, just for the sake of logistics, what we will do is we will go around the panel. Each person will talk for about 4 or 5 minutes on their slides. Then we will have a discussion as Pawan suggested, and finally we will throw it open to audience questions, okay?
Okay. Okay, so I'm going to tell you about inflationary cosmology, which is what I have been working on in the last few years as far as astrophysics and cosmology is concerned, or more precisely, which is what my students, in particular Farman and Suprita, have been working on in the last few years. If you have any detailed questions about any of this, you should ask, in particular Farman, who just almost graduated yesterday. He had his pre-synopsis yesterday, and of course Suprita, who is also presenting a poster outside. Okay, so as Orko explained, the standard accepted wisdom is that the universe started with this inflationary phase, where there is extremely rapid expansion, exponential expansion of space at the very early stages of the universe. The metric, the space-time metric during inflation is approximately a de Sitter metric, which is given there. At the end of inflation, we compute the correlations of fluctuations of the inflation field, inflaton field, which is a hypothetical scalar field that was responsible for the rapid expansion, and then relate these correlations to observable correlations of temperature fluctuations in the CMB sky. So our observables are these correlations arise from quantum mechanical fluctuations of the inflaton field during inflation. So schematically, this figure shows that you have correlation. You start from some initial state and then evolve, and finally have some correlation at the end of inflation, and then you run some machinery to translate it into information about temperature fluctuations at the CMB. As I told you already, the accepted belief is that quantum mechanical fluctuations during cosmic inflation led to temperature fluctuations observed in the CMB sky. And later, these fluctuations are also imprinted. The consequence of these fluctuations are imprinted on the structure formation, on the structures which we see today. And indeed, the story of the origin of density perturbations from expansion of universe, stretching quantum fluctuations out onto enormous distances, is one of the most spectacular stories in all of science. Now the question is how we compute these correlations. Now, as I said, the standard belief is that these correlations are generated quantum mechanically. And as you know, in quantum mechanics, if you know the initial state and if you know the interaction Hamiltonian, you can compute the final state, and at the final state, you can compute some correlations. So that's what we do. So what we need to know are two things: initial state and interaction Hamiltonian. So the core questions in cosmology today are these. What is the initial state of inflation? There are very good guesses for what the initial condition could be, but there is no concrete proof of this, and I think we are quite far from knowing what exactly the initial condition was at the beginning of inflation. Then we need to know the interaction Hamiltonian, which basically means that we need to know the fields and particles which existed during inflation. Now let me tell you that this is very similar to what one does in high energy collider physics also, where you want to know the heavier and heavier particles and how they interact. So there you collide particles and then try to figure out whether there are new particles. Now here things are more complicated because we cannot collide anything. In fact, we cannot even talk about scatterings. We can only talk about some observables which we measure at the end of this evolution. So let me let me tell you just one important aspect of this as against particle physics. Here in cosmology, actually there is no time. If you think about it, cosmology is a field without any time, because what we measure are some spatial correlations at the CMB sky, and then from that we try to infer the existence of a past. And then through a set of logical rules, we try to see whether this is consistent with some time evolution starting from an initial state. So that's what we do in cosmology. This is very similar to what paleontologists do, people who work with fossils. They find some big bones, then small bones here and there. These are all spatial patterns. And then through some logical rules, they try to reconstruct the history. If they see some big bones or some small bones inside a big bone, they see that, okay, maybe, there's a big animal who ate a smaller animal and so on. So here also we are exactly trying to do the same thing. So in that sense, cosmology is one of the most, grandest historical sciences. And that's what exactly we try to do. We see some spatial patterns, and then first we try to infer the existence of time, and then through some self-consistent logical rules, we try to reconstruct the history and see whether what we see at the end of it is consistent with what we observe. Okay, so the third bullet is, can one prove in a more rigorous way, through cleverly designed observables? For example, one could think about cosmic Bell violation, which has been talked about in the literature but without much clear success, whether the accepted belief that quantum mechanical fluctuations during cosmic inflation led to temperature fluctuations observed in the CMB radiation is indeed correct. Because this is a very tall claim. We see these fluctuations at very large distances, as Orko mentioned, megaparsecs, hundreds of megaparsecs. Now you'd naively think that quantum mechanics has no role to play here. But we are claiming that these fluctuations, which we see at extremely large distances, they are also coming from quantum mechanical fluctuations, which usually we think is something relevant at very short distances. So this claim that these fluctuations are quantum mechanical, this is a very, very strong claim, and for such strong claims one needs very strong evidences. So while what we understand today is that this claim is consistent with a quantum mechanical evolution in some specific model framework, but there is no model independent way to prove this. At this, I think nobody has come up with such a model independent way of thinking about it. And finally, there is hope that inflation, if there's something called the gravity wave coming from inflation is measured or can be measured. There's possibility that it will be measured in next n number of years. N can be small, large. I don't have much clue. It might tell us about the nature of quantum gravity, at least something about quantum gravity. This connection is not exactly clear-cut, but we may learn something about quantum gravity if we actually see inflationary gravity wave, which in the literature called the tensor to scalar ratio for inflation. There are many others more, detailed and important things, but I think in my, subjective opinion, these are the broad questions we are interested in inflationary cosmology, and at least this is what I have been interested in recent times. Thank you.
So my talk will be a bit less technical because I think all the techniques will be discussed. Already Pune has given all the details, and rest later who are going to come are also going to give some details. So my talk will be just to see how to connect various things. I'll start with this slide. This I generated from ChatGPT. Dhruva, my student, gave me idea that you can use ChatGPT. You have to keep on writing on ChatGPT, and then it will produce some nice picture. Also, the overall idea about detective and this way of saying cosmology may not be mine. I think it is not mine. I might have heard or read somewhere. Also, whatever I'm going to talk is based largely. I have done some work with my student Arum mainly, and with Sahil, who is a fifth year student, Arvind, who was a previous fifth year student, with Orko some work, and thousands of beautiful papers. Okay, so what do we? Most of actually, I at least enjoy detective stories. I think many of us enjoy. So let's say crime happened yesterday, and I just look at the clue today. I have to say what happened 1 day ago. That might be a little easier problem, because you can still the clues are new, and then you can find out the clues and find out what happened 1 day ago. Let's do 1 year ago. Then it's a little more difficult. Let's do 50 years ago, which we have heard about. There are serial killers, etc., who has never been caught, because those are very, very difficult, and they leave very less clues. But let's say I have a story which we want to understand a crime thriller which is like 14 billion years of old. Something happened 14 billion years ago. All you have access to is today. You see whatever, and then you have to construct the whole history. Okay, it's not entirely true. We see today and then some part of previous thing, but a lot of part is not accessible to us. Still, we have to figure out what happened previously. So as you can see, it's already a significantly challenging program. And as you know, a good story will come with a lot of details. Most of the boring stories, they don't show details, but here in science, it's great that we have a lot of details, try to stick to various things. But depending on the storyteller, he will focus on only few of the details. Okay, that is what I'm also going to do. This picture I don't have to discuss now, because already Orko has already discussed that there was a Big Bang some time ago. There was a Big Bang that happened. That's a usual picture, inflation. Then you see CMB here. If you can see cosmic microwave radiation, that is something that you can observe. So until that thing, as you know, there are 4 forces in the nature. Until that time, gravity played some role, but all the other 3 forces, strong, weak, electromagnetic, played very important role. And then finally, they give rise to cosmic microwave radiation. And gravity was just sleeping, more or less sleeping till then. And then suddenly wakes up, and they said, I don't care about rest of the people. Now I'm going to dominate you, and I'm going to show you how to dominate. So what it does, it takes all those, as Diptimoy was explaining very beautifully, that cosmic microwave radiation that we see, there is a temperature fluctuation. Those are not all even. Like the densities are not really even. So wherever there is a large density, gravity will pull together other things, and once it pulls together, slowly over the time, it's a big lot of time. With that, slowly it works and starts creating the galaxy. Okay, so this is the picture where I work on looking at the cosmic microwave background, theoretical aspect. By looking, I mean theoretically looking, not experimentally. And there I use something exotic, which is conformal field theory, which is a theory to understand, let's say, second order phase transition, to understand the correlations as Diptimoy was pointing out. The other aspect I have recently started looking with Orko, Arhum, Sahil, and other people is to look at what happens in the large scale structure, which are, mostly it gives us a clue about how the dark matter, etc., are distributed. In order to actually pose my question, where I'll stop, I'll just take an analogy. It's a digression. Take molecular picture of water, and then there is water wave. Let's say I ask the following question. I want to understand how the water wave forms. Would I be interested in understanding whether the water is formed out of hydrogen atoms or oxygen? I may not be interested. Rather, I would try to see, I don't care about how the molecules are formed. I'll try to see how the molecules actually collide with each other. As you know, one of the theories, Navier-Stokes equation, which describe effectively in the large scale how the water flows. The other picture is molecular picture, where the various molecules, how do they collide. Here in the large scale structure, it's precisely similar thing happens. You can either take molecular picture, which will be like the simulation, which Orko will be discussing, or you can take the water wave kind of picture, Navier-Stokes equation, to describe what is happening. And I mostly work on this later picture, where I use some effective theory to describe the distribution of the galaxies, etc., etc. Now, given this fact, you can ask following questions, which are the questions that I mostly find very interesting. Let's say if I ask, given the molecule, let's say water, given the water wave, or given I know the knowledge of large scale structure, the water wave, shear viscosity, etc., etc., can I understand something about molecular picture of the water? Okay, that's the question that suppose you want to ask. How will you phrase that question in this context? Here you will phrase the question is that given the distribution of galaxy, as you will define more precisely, is there how do I know about much earlier physics, which is cosmic microwave background? Given the cosmic microwave background, do I know what happened in the Big Bang? Was that Big Bang really there was a singularity? String theory says, for example, there is no singularity. It goes into some Brent-Wald construction, Higgs-Dronne phase transition, etc., etc., to describe what happened at the beginning. Depending on each model, the CMB will be different, as well as what will the large scale structure will be different. So the question that I am interested in, given the initial what happened, either string theory or Big Bang or whatever classical picture, quantum initial state, what are the subsequent things? Are they all determined? How are they determined? Or let me reverse the question. Given I know the large scale structure, let's say water wave structure, which is in this case galaxy distribution, do I know, how much do I know about the cosmic microwave radiation? How much do I know about the initial stages? Maybe a string theory, or maybe Big Bang or something. These are the questions that I'm mostly interested in and looking into. Okay, thank you.
Carrying on from where Sachin left off, so we see the universe both in its early state, which is the cosmic microwave background, as well as the late state. So the late state on your right is basically if you take a telescope and point it out towards the sky, this is what you will see. You will see lots of galaxies and so on. So basically we want to understand the evolution of the universe from the early state, the cosmic microwave background, to the late state. And this is what allows us to understand the underlying cosmological model, its ingredients and its parameters. So a partial list of science questions that can be addressed by understanding this connection, some of which has been referred to already. I have ordered it in my particular order of favorites, is the total mass of the standard model neutrinos, which is extremely light, actually leaves a measurable imprint on this evolution. We can try to understand the microphysical nature of dark matter. So there are lots of lines of evidence which tell us that something like dark matter exists, but what it is one of the biggest questions in all of physics. Related to this, is there only one type of dark matter, or is there a dark sector? So like the standard model is extremely complicated in some sense. Is the dark sector also complicated? There's also, we can learn about early universe physics, as Diptimay said, at energy scales far beyond the reach of terrestrial experiments. So inflation, the scale is roughly 10 to the 15 GeV. There's no way we are going to reach that with terrestrial experiments. Finally, you can ask, what is dark energy? So is it consistent with being the cosmological constant of GR? Or do we need to invoke something else to explain dark energy? So those are the list of questions that we are all broadly trying to answer. Now let me come to what I have been working on, or I work on with my students. So the first thing on the left is whenever you come up with a new model, let's say you want to complicate the dark sector, you not only want to know what happens on large scales where, like Sachin said, effective field theory techniques can be extremely useful. You also might want to know what happens to structures or the nonlinear structures that form due to gravity. Because as Sachin was saying, anytime you let gravity go, Even if you start off with small fluctuations, gravity will at some point drive them nonlinear. To follow these nonlinear structures, you need simulations. You can't get away from it. And the simulations that are typically employed in cosmology are called n-body simulations. So one aspect of my research is to develop simulation techniques for exploring these new models of cosmology. Okay? What happens, to understand the effects of neutrino mass on large-scale structure or how galaxies form, you need to be able to incorporate the neutrinos self-consistently into these simulations. How do you do it? You might want to complicate the dark sector, so you might want to add other massive relics, which are not the standard model neutrinos, into your cosmology. What numerical techniques do you need to do this? Dark matter can have not only gravitational interactions with other particles, but can have strong interactions within the dark sector itself. This is called self-interacting dark matter. Again, how do you modify the simulation techniques that people have been working on for the last 30 years to expand the range of models that you can actually access, you can study in detail, and then compare with observations? Okay. So this is one aspect of my research. On the other side, we have these billion-dollar experiments which are all looking up at the sky at different wavelengths, trying to measure the universe as accurately as possible. And you might ask, what is the maximum amount of information about the universe I can access by looking at, let's say, the distribution of galaxies? So that picture on the right there, someone gives me a list of galaxy positions. I measure a galaxy here, 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 here. What is the total amount of information in that picture? So what a cosmologist would do would be to measure the two-point correlation function of that picture and then try to get as much information as they can from that. But if you look at that picture, the field itself is highly non-Gaussian, so a two-point function of that field does not tell you all the information that lives there. So one of the main goals of cosmology, especially driven by the large-scale structure surveys that are online, is to come up with summary statistics which go beyond this two-point function or the Gaussian part of the information to optimally extract whatever we can learn about cosmology from just these pictures. So what I've been working on in the last few years is a particular summary statistic called the k nearest neighbor distributions, which we have shown along with many people in my group is extremely useful at extracting the non-Gaussian part of the information from these images. So the triangle plot at the bottom is supposed to represent how much better our constraints become when you use these statistics compared to the two-point function. There are many interesting aspects to explore here. There's a theoretical aspect, what do these summary statistics mean? What are their geometrical topological implications, but also how do you apply them to different data sets in cosmology? And as with many other things, it ties directly into machine learning. So if you showed the same picture to a machine, would it be able to learn more than whatever human interpretable statistics that we can come up with? And if it does, what are the humans missing? Okay? So these are roughly the broad techniques that I work on, and those are the sort of questions we are trying to answer by applying these techniques. Okay? And so next.
All right. So good afternoon, everyone. So I think it's going in a very nice sequence. I think we started off with talking about the small fluctuations, the origin of the fluctuations in the different energy density fields in the universe, which Deeptimoy was talking about at the time of inflation, Sachin was talking about at the time of CMB. Where I will add on to this is I will be talking about the endpoints of these fluctuations, okay? So we know that we think that the universe, as we are observing it today, the observed universe, the distribution of galaxies in it, the distribution of matter in it, originated, we think, from these quantum fluctuations, right? Which were basically inflated during a period of rapid expansion, and they laid down the spectrum of fluctuations in the matter fields, in the temperature field in the universe. And what I study is the evolution of these fluctuations into, in some sense, the endpoint of particularly the matter fluctuations, which are basically driven by the gravitational evolution of matter, okay, of matter perturbations. And those are dark matter halos, okay? So, so that's sort of like the chronological story of the universe that we tell ourselves, but this is, of course, a model that we have created to explain the observed universe. So to step back, the inference that there must be something like dark matter in the universe actually came from observations of very local, in some sense, not as local as the scales that Prasad here works on, but in some sense of the very local universe within, in fact, from the observations of galaxies that are dwarf galaxies that exist around our Milky Way galaxy, right? So to understand the dynamics of gas and stars within these galaxies, we realize that we need something. We need an additional gravitational component to explain the behavior, to explain the motion of gas and stars in these objects. So that was initially sort of the emergence of the idea that something like dark matter is essentially needed to explain what we are observing in galaxies that are very close to us, and not just in galaxies that are very close to us, also in clusters of galaxies. So when we saw groups of galaxies which appeared to be bound together, we needed to invoke an extra gravitational component to keep these galaxy clusters bound and not have them sort of fly away from each other. And it was basically observed that you can't just have all of the gravitational mass tied to the light in these galaxies, to the stars in these galaxies, to keep these systems bound. Okay? So the inference, so what this was implying is that these stars or these individual galaxies that appear to be bound in a cluster need to exist in some kind of a gravitational potential of a kind of matter that does not seem to be emitting light, or we cannot observe it in our telescopes, either way. So I think these objects eventually were called dark matter halos, and that is essentially what I spend most of my time studying. Now, one of the aspirations of cosmologists or physicists in general is to understand this large scale, not only infer and construct models, but we also have to understand whether the models of the universe that we are constructing are consistent with a wide range of observations. And I think one of the greatest success of the current model of cosmology has been that these models with the three pillars of cosmology, which is dark matter, that we need something like dark matter, that we probably live in a universe that is expanding in an accelerated way, and all of this originated from something like inflation, tends to explain not only the local distribution, local behavior of galaxies, but also the spectrum of fluctuations that we are seeing in the CMB, for example, right? So it's been one of the successes of this model to explain a wide variety of physics on a wide range of scales. So observationally, at least, we think there is ample evidence for dark matter. We think that this dark matter that seems to control the dynamics of the visible matter in the universe is cold, collisionless, and interacts only through gravity, okay? So this, by cold, we essentially mean that the dark matter, this invisible component, which is basically conspicuous in its absence, needs to have very low thermal velocities. It is mostly dictated by its bulk velocity. It is largely collisionless. It does not interact with itself. It does not seem to interact with itself or with other baryons or visible matter in the universe with very large cross sections, and it primarily all the structures that we see can be explained by its gravitational interaction. And we think that most of this dark matter, which dominates the gravitational component in the universe, lives in these highly nonlinear, gravitationally bound objects called dark matter halos. So as I was saying, these are the endpoints of fluctuation. So these small fluctuations in the early universe in the matter perturbation, they basically, because they are matter perturbations, they have gravity, so they tend to collapse onto itself. It tends to attract each other. So eventually, as these matter perturbations grow, at some point, these matter perturbations become nonlinear, or rather, they essentially collapse gravitationally and become gravitationally bound. So these halos are gravitationally bound regions of space, which are essentially, in some sense, disconnected from the rest of the expansion of the universe, okay? Because they are bound within their own gravity, okay? So what I try to understand is, even to start off, even in the vanilla scenario where cold collision, if we consider dark matter to be cold and collisionless, which is largely successful in explaining the large-scale structure of the universe, which Orko and Sachin were talking about, how does this cold and collisionless matter reach a state of equilibrium? How does it actually distribute itself inside of these dark matter halos? And can we actually test this? These models make some very specific predictions about the distribution of dark matter inside of these collapsed objects, and can we actually go out and test them, right? So that is one of the questions that I spend my time working on. How do halos assemble from these initial fluctuations in an environment of other fluctuations, in the tidal fields of other halos that are growing and evolving with it, okay? How is the matter distributed inside of them? And central also to this question is how is the formation of galaxies related to these to the evolution of dark matter? Okay, and this is both sort of an observational and also an empirical understanding that if most of the matter in the universe is dark, then they basically form the potential wells within which galaxies form and evolve, right? So they dictate, their gravity not only dictates the distribution of the overall dark matter in the universe, it also dictates the distribution of other gravitating things which do emit light, like our standard model particles, and these galaxies evolve in the potential wells of these dark matter. So one of the other questions that I try to think about with my students and my collaborators is essentially how do galaxies evolve in these potential wells, and can we, and this is also, while we're talking about in the cosmological sense, very small scales, so the halos that I think about are on a megaparsec scale, whereas our observable universe is about 13 gigaparsec scale. So this is 1,000th of that, 1/10,000th of that scale, right? So even though the physics of large-scale structure is happening on a larger scale than the structure of these halos, which are essentially isolated from the expanding universe, the evolution of their evolution is central to understanding the large-scale distribution of galaxies in the universe, right? Because we need to understand, because a lot of the inference about the large-scale structure and the large-scale evolution of the universe comes from the distribution of galaxies on large scales, because they are essentially the things that we can see, right? Therefore, it becomes essential then to understand how these galaxies populate the dark matter potential wells across the universe that we observe. Okay, so that's one aspect of what I think about, and you can ask me more about it or my students when you find them. And lately, I've also been interested in trying to understand, while one aspect of the universe is the stationary, of the observed universe is the stationary, everlasting galaxies that we see in the sky, there is also a transient universe, okay? And now we are really starting to get a new window into the universe through the merging of binary black holes in the universe through gravitational wave observations. These stars, these binary stars or black holes or neutron stars have also evolved and formed in the galaxies that we see. So one of the things that we are trying to understand is how these gravitational wave sources trace the large-scale structure of the universe and what we can learn from their distribution, from the distribution of these gravitational wave sources about the underlying evolution in the universe. And in some sense, this is also a consistency check that if we think that all of the matter is tied to the dark matter distribution, is tied to the standard model particle distribution in the universe, then the large-scale distribution of these binaries that we see in the universe should also be consistent with our current models of cosmological evolution, of galaxy formation, and so on. I think I've exhausted my 5 minutes, so I'll stop here, and I'll leave it to Prasad, who will go to even smaller scale.
Sorry, before Prasad comes on, I'll pretend I'm Arun Thalapillil. And for the sake of completeness, this is Arun's slide for the... Yeah. So I'll quickly go through this. So Arun looks at astroparticle physics, looking for new particles, new interactions, astrophysical compact objects, so things like the central black hole of our galaxy. He does this to explore new regimes of quantum field theory which may not be accessible from terrestrial experiments. And these compact objects can also be made up of things that we do not usually think of. They can be Bose stars, primordial black holes. They can have magnetic monopoles in them. And all of this physics you can try to do by looking at observables within the galaxy, whether it's through microlensing, through measuring the central black hole very well, and things like that, okay? So all of Arun's stuff up here. In the interest of time, I will hand over to Prasad. And I will...
Thank you. Excellent. So, yeah, I've got a movie. Yeah, I'm the only cool guy here. The rest of you, all boring equations. I work in a couple of different areas. So I worry about what the sun does to our immediate space environment, okay? And no better way of illustrating it than this. You see, what's at the very center there is the sun, okay? There's a suite of different instruments, and the Earth is here and there. This is real data. This is not a simulation. This is real data. So this is data from two satellites, like our two eyes. And so what you've got here is what our two eyes are seeing, sort of spread out on the screen. And so what you can see here is a puff of smoke coming out from the sun, from the solar corona to be specific, coming out, and you see it's coming, it's hitting the Earth at some point. It's hitting the Earth here and there. So these are called coronal mass ejections. And most of what I do, about 70% of what I do, I worry about these things. Why are these important? So you can see that, I don't need to say anything, you can see it. Okay, a very rare, it happens all the time, but this kind of detail you get only rarely. You cannot see it very. I use data. So why is this important? This is important because these coronal mass ejections, when they interact with the Earth's geomagnetic field, they cause what are called space weather disturbances. These days, thanks to a lot of press coverage and everything, yeah. So you would have heard about these things. These are called geomagnetic storms. Why is that important? That's because most of our satellites, on which a whole lot of our very technologically dependent life. Imagine what would happen if you lost GPS, or horror of horrors, if your cell phone didn't work. You weren't able to watch your YouTube videos for like, I don't know, 2 seconds. I'm kidding. Okay. Yeah. But really, I mean, if GPS, if you've got a GPS outage, and this is a very real occurrence during episodes of large geomagnetic activity, GPS signals are severely affected, especially over equatorial regions like where we live. So what I worry about is how these coronal mass ejections interact with the Earth's magnetic field, and it's a very complicated chain of interactions leading to a whole variety of effects, all collectively called space weather. Very much like terrestrial weather, except this is in the immediate vicinity of say, about anywhere above about 600 to 700 kilometers above the Earth's surface. This is where our satellites live, so it's very important to understand. So the kinds of, some of the, so these are some of the key questions. How, so specifically what I work on is I try to understand how the coronal mass ejections propagate through from the sun to the Earth. Basically, equation of motion, F equals ma, as simple as that. Except you can write down the equations. You need to know what's, you don't know what the F is, you don't know what the A is, so you need to figure it out. And we are still fairly far away from doing these things. Why do you need this? I get a total of about 5 phone calls a day, and one has to come during this time. So you see, one of the things, surely you're aware of parachute, aerodynamic drag on a parachute. A parachute drops down, and beyond a point, he or she attains a terminal velocity. So it's very similar to that, except the solar wind, the medium through which the coronal mass ejection travels, is collisionless. Similar to collisionless dark matter, as in, except much less exotic. The particles are spaced way too far apart. Okay, so the length scale, so they rarely get a chance to collide with each other. So if you don't have collisions, where's the fluid? I mean, how can you, what's dragging it? So these are the kinds of microphysical questions I worry about. And specifically, I use observations obtained by satellites stationed near the Earth. And these observations you can think of as like a little needle, okay, making observations of a huge haystack, okay, humongous haystack. You've got detailed observations, but just at one point. Okay, so you've got a time series, and it gives us some information about turbulence. Turbulence is a very important ingredient in all of this. So how does turbulence play a role in triggering these geomagnetic storms, so on and so forth? And yeah, that's about. So having said this, I also work on black hole accretion. You might wonder the physical circumstances are very, very far apart. Turns out that black holes, the way they accrete matter, is it's believed to be. You never know what's going on there. But still, the plasma around the black hole is also thought to be collisionless. So the same sort of mathematical techniques, as one of my good collaborators says, when you've got a hammer, everything looks like a nail. So you just apply the same old stuff. So I worry about things like viscosity. That plays a central role in sucking matter onto the black hole. I worry about the same kind of viscosity that acts on coronal mass ejections to slow them down. The same old. But whether or not the governing equations are appropriate or right, or they are there, I solve them, I scratch my head, I hope they are right. And if they're not, hopefully there will be some warning flags. So this part of my research is very data heavy. I use honest to goodness data, not so much here. So that's all I have to say. Thank you.
So in the interest of time, maybe we can move on to audience questions to increase the interactions, or?
You have everything in agreement among yourself.
Is that an audience question, or?
Yeah, you can actually.
Organizer question.
Yeah, in fact, we have probably about 10 minutes or so.
Yeah,
we can. The actual progression is that there will be a shorter presentation and a longer discussion. That's the progression of the other panels which will happen. But in this particular case, of course, you actually got a broad overview. So we'll throw it open for further questions. Please, we strongly encourage you to ask as many questions as possible, because after 10 minutes, we'll take all these things outside, because there's also things which are happening outside. But we do encourage people to ask questions. We can start from there on that side. Is there any question on this side? Yeah.
So Thanks, Prasad. Uh, as we know, yeah. So there is 2025, and in this year there is coronal mass ejection from the sun, and people are expecting that this time it is going to be very heavy or maximum, so it can disrupt our all the kind of GPS system that you said, right? So how and what scientists are going to do against these all coronal mass ejection?
Yeah, very little, frankly. Not much you can do. You just have
No,
to be aware.
look, no.
Let me elaborate.
My concern is if there are asteroids that are going to come near the Earth, and people are expecting that do some kind of nuclear blast in the space, and they are going to
Yeah.
So in that sense, how and what people are
Sure.
thinking?
Sure. A lot of quasi science fiction there, asteroid mining and things like that. I don't know. I'm quite skeptical. But yeah, I mean, as far as CMEs are concerned, again, not much you can do really. But you can be aware. You can have accurate estimates, time of arrival estimates. You can have accurate estimates of the strength of the geomagnetic storm that is going to it's going to trigger. We are far away from good estimates. Okay, having produced those estimates, you do the best you can by way of shielding your satellites. You close your doors, you put your satellite in safe mode so that the instruments inside are affected to the least possible extent. When GPS outages are expected, if you've got pilots flying right over, you give them warning so that they switch to redundant systems, so on and so forth. So it's all about forecasting as accurately as possible and bracing yourself for the impact. That's literally, yeah, no way of preventing these things. Just as I believe there's really, I mean, there might be a 10% chance of pushing an asteroid away, but yeah, awareness is key. That's basically, yeah. In fact, there's a whole field called space situational awareness.
Hi. Seeing in the slide that correlation in the temperature fluctuations that you propose to be of quantum origin, I didn't get the reasoning. Why are you saying so? And second question is, correlation is something that can be measured, that can be analyzed very quantitatively, whether it's of classical or quantum. For spatial correlation, we have Bell's or more generalized CHSH kind of inequality. For temporal, we have Leggett-Kirk, or then temporal CHSH inequality. So why, if we have the data, then is there any quantitative analysis that has been done to answer this question?
Maybe I should collaborate with you to see whether one can find, no, seriously, so one can find some Bell inequality violation for correlations. You see, these are just correlations, they're not some scattering matrix elements. They're just correlation functions, spatial correlation functions. At least I don't know a good way of defining an observable, which is a very, and make a statement that, if this observable has value this, more than this, less than this, or whatever, then this tells us that the origin of this fact that the observable has value more than this cannot be classical. It has to be quantum. So in the cosmology context, I don't know of any such observable which one can easily measure. Okay, one can measure. As you know very well that this is not the case for say scattering, for 2-to-2 scattering. In fact, Bell violation has been tested also for 2-to scattering, even for high energy scatterings. So that's why I said that there is no concrete model independent way of, as of now, of showing based on observations that these correlations originated from quantum fluctuations. Say, for example, why not thermal fluctuations? You see fluctuations. They could be due to thermal fluctuations. Now your first question about why people think that they originated from quantum fluctuations. This is mostly due to the fact that we know how to compute these fluctuations in a well-defined quantum mechanical setup, and that we have done, and the answers we get, they agree with what we see. Say, for example, for 2-point temperature fluctuations, what we see observationally is that they are not completely random noises. They are scale invariant, in the sense that if you see the 2-point fluctuation as a function of the distance between the 2 points, then the variation with respect to this distance is very slow, is logarithmic. Now, this you can understand from a in a setup. Yeah, so in a setup where we know how to, the exact rules of calculations, start from some initial state, calculate and get to this point. So, in a model setup, we know how to compute it in a quantum mechanical calculation. But if we don't assume that model, if there is an independent way of checking, like Bell violation, that you make this measurement and say very confidently that if this inequality is satisfied or not satisfied, then the answer cannot be coming from a classical evolution. It has to be quantum mechanical. This kind of statement for cosmology is still lacking.
Hey, thanks for the wonderful overview. I think Deeptimoy mentioned that the large-scale structure of the universe and the quantum fluctuations in the early universe that we indirectly observe in the CMB were related, and also Sushmita said that the galaxies are formed where the dark matter halos were there, and so the galaxy formation in the large-scale structure is determined by the dark matter density. So I wanted to ask, are these two pictures overlapping?
So I think, right, so what we are trying to say is that so we want to understand, so we have the, say, CMB, right, and we measure the 2-point correlation function of the temperatures, which is basically telling us how the fluctuations in the CMB are distributed. At late times, so CMB was early times. At late times, we also see the galaxy distribution in the universe, the spatial distribution of galaxies in the universe. We also try, in a very similar sense, in large-scale structure, maybe Orko can talk about this, the distribution of galaxies we can also measure the correlation function of the distribution of galaxies. And what we try to do is we try to connect that early picture, evolve it with gravity to this late time correlation function of the structure of the galaxies in the universe. Okay, so that's how we try to understand the distribution of these temperature fluctuations and relate them to the distribution of galaxy fluctuations in some sense, and make that connection and can we build a consistent story starting from the early universe to the late universe as we see it. Yeah.
Yeah, so actually that is the whole, that is what the success of this program has been. That this model where you have inflation laying down the initial spectrum of perturbations, along with just the standard model matter, something called dark matter, and something called dark energy. Just with these ingredients, you can follow the entire universe's evolution from the initial perturbations to the pattern in the CMB, to the structures of galaxies and large-scale structure that you see today. For the large scales, you do not need to invoke anything else. In the CMB, you see where the baryons are, not where dark matter is. At late times, you see where dark matter is through the galaxies. But the same underlying model, which we call lambda CDM, which cannot be complete, so there is lots of work to be done there. The astounding success is that it explains the entire evolution of the universe. You need no other ingredient.
Sorry, I'll just take 1 minute to just add one thing that, if you just take the CMB temperature fluctuation, which is somewhere overdense, somewhere underdense. If you don't have generally dark matter, you will see only baryons, etc. Then probably you will not be able to actually construct the galaxies just in that picture. So generally dark matter is required. Now you can ask the, so it relates both of your question. You can also ask like dark matter, do I require before the CMB or after the CMB? There are a lot of debate about it. Like there are WIMP and then there are axion dark matter, etc., which are at different regions. Like some covers most.
Yeah. One final question.
So 12 years ago, there was some claim that these tensor scalar perturbations were seen or B modes by this BICEP 2 experiment, and turned out to be a wrong experiment or wrong interpretation. But I think Diptimai said that we are going to see these modes, gravitational perturbations. Is that what you said in the future?
We measure them in the next years.
So my question is like, what is the hope of measuring these perturbations by some other experiment, and how soon?
Yeah, so I think this question can't be answered because you see, it depends on the actual value of this object R. Now, if it is at the so we have a bound that R less than some, let's say 10 minus 3. Now, if it is very close to 10 minus 3, we might be able to measure it soon, but we don't know how small it is. If it is extremely small, we will never measure it. So.
So yeah, there are multiple ways to do this. One of them is, so you keep measuring the CMB power spectrum more and more accurately. Not just the CMB temperature fluctuations, but the polarization of the CMB. And so there are proposed experiments like CMB stage 4, which will be hopefully operative in the next 5 or 6 years, which should be able to do this. There are proposals called CMB HD, which are expected to be in the 2040s, which might go down even by one more order of magnitude. But as you know, these are all, at various stages of its passage through NSF and DOE. So we don't know what is going to happen.
The last. Yeah. So thanks, Pawan. I have a very, because of layman, I am a layman in this field, so I have a very naive question. The question is that I thought matter and energy are connected. They are the same thing. Now here I see that you are talking about that much dark matter, but that much amount of dark energy. So are they not connected?
On a lighter note, you see, matter and energy, they are connected, but dark matter and dark
so
energy,
basically you don't know
not connected.
So they seem to have slightly different behavior. So what we call dark matter
is not a matter.
Is not part of the standard model for sure.
Okay, but it is not a part of the E equal to mc square also?
No.
So then where does it connect?
So dark matter and dark energy refers to slightly different things. Dark matter is something which gravitates like regular matter. So it seems to be non-relativistic, pretty heavy. A pretty heavy particle would act like dark matter as long as it does not have any electromagnetic coupling.
But as a matter and energy, that interconnection is not yet there.
No, yeah. That all of that is true.
But then how do we know? We say that okay, that much is dark matter, that percentage and that percentage.
Dark energy is what is responsible for the accelerated expansion.
So what is the connection between them? There has to be connection between them.
No. They are two.
Not have to be
these are two different entities. The fact that we call them dark matter and dark energy is just language. We could have called them dark matter and blue energy.
Okay. So it is not.
They are different entities.
Of E equal to mc square. That understand?
No, they are. Yeah. Einstein's equations hold.
Okay.
But these are two separate entities that contribute to the. Yeah.
All this matter can be taken outside now. we have plenty of time. Okay. No. It's fascinating. It's a good start. See, this is also a new format. We are getting used to it. This is also a self-iterative process, and let's thank our colleagues for setting up this. It's a tough thing, As you know, in test match, the opening is always difficult. So therefore, thank you very much. So we break for roughly about 24 minutes now. We regroup at 4 o'clock for atomic molecular optical physics. And there are posters. Please go ask questions, interact.